So question 200. Wow, this is the last question from the Year 2 A-level syllabus, and it's probably one of the longest questions of all of the 200 as well. So pay attention, and I hope you've got enough stamina to get through to the end of this one. So we can see the acceleration here is a function of t. So it's not constant acceleration, so we're going to need calculus rather than suvat. Part A is asking us to find the time when the particle p is moving parallel to this vector. So we need to find an expression for its velocity. Now, velocity is the integral of acceleration. So there's our acceleration. We're going to integrate that. And when we integrate 3t, get 3 over 2t squared, and minus 1, there's a minus 1 there, integrates to minus t. But we need to add the constant of integration, and the constant now is not just a number, this is a vector. So how do we find the value of the constant? Well, we know that when t is 5, the velocity is 5i plus 2j. So that's been given to us. When we substitute t equals 5 there and there, then this will equal 5i plus 2j. So there's our equation. From that, we can take these items over to there to find that c is that. So when we put that c back into there, we get our final version of the velocity, and grouping the i's and the j's together gives us that. So there's our velocity vector. Why did we need that? Well, we wanted to find the time when the particle is moving parallel to this vector. So when this vector is parallel to this vector, it must mean that the I component and the j component have got different signs. So therefore the I component is the negative of the j component, or vice versa. It doesn't really matter which way you do it. So we get, there's the I component there, and there's the j component there. And so that gives us a t of 4.47 seconds. We do get another answer to this equation, which is a negative value of t, but we're taking positive values of t. We're not going into negative time. So that's part A complete. Now we look for the speed of p when the j component of its position vector is 0. So we need to find an expression for the position vector. So the position vector is the integral of velocity. Now we had velocity on that previous slide. That's the velocity vector. And when we integrate that, integrating 3 over 2t squared gives us a half t cubed, minus 32.5 goes to minus 32.5t, 7 goes to 7t, and minus t goes to minus half t squared. But we still need to remember that we're adding a constant, which is a vector. How can we find out that constant? Well, we know that when t is 5, the position vector is minus 15i plus 8j. So we're putting 5 here, 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 and here, and we're making that equal to minus 15i plus 8j. And thank goodness for calculators. That gives us that expression for c. So when we put that there, we get this as the position vector of the particle at any time t. The value of t that we're interested in is when the j component of that position vector is first 0. So we want to make that equal to 0. We'll get two answers, but it's the first one, the smallest positive one, that we're interested in. And that's the value of t there. The other value would be 7 plus 2 root 5, so it has got a j component of 0 later on as well, but this is the first time. Putting that value into the velocity vector, because we're trying to find the speed of p when its j component of position vector is 0. So there's our velocity vector, which is that, and then the speed is the magnitude of the velocity, which is 23.3 meters per second. So that's part B complete now. Let's look at part C. We want to find the distance when t is 3, the distance to the origin. So the distance to the origin is the magnitude of the position vector. There's the position vector from the previous slide. And when t equals 3, we get that, which simplifies rather neatly to I plus 2j, and then the distance is the magnitude of that vector, which is root 5 meters. So there we are, question 200.